Hi, this is an example problem from chapter 11 that has to do with Archimedes' principle. Pause for a moment and read the question. So in part A, we're trying to figure out whether this raft floats in the water. Of course, we assume it'll float, otherwise we shouldn't call it a raft. But to try to understand this, we're going to do a free body diagram of this raft to understand what's important here. So here's a little dot for representing the raft, and we've got the long-range force of gravity, of course, which is going to be pointing straight down. That's the gravitational force that acts on the raft due to its own weight. And then we've also got some upward force if it's going to float, right? That upward force is going to be called the buoyant force, right? And if it floats, those two are going to be equal, right? And so we have to ask ourselves, what's the maximum buoyant force that we can have, right? If the maximum buoyant force is less than the gravitational force, if it's something like this, it's not going to float, right? However, if the maximum buoyant force exceeds the gravitational force, or at least equals it, then that object can float. So for part A, let's figure out how we can determine the maximum buoyant force. So Archimedes' principle tells us that the buoyant force, FB, that is equal to the weight of the water that's been displaced by the raft entering the water. Now, the maximum buoyant force you get is if you push the entire raft into the water. Imagine if you have a beach ball at a swimming pool. If you try to push it down, the further you push it into the water, the more it wants to push back up with force, right? That's the idea here. Now, according to Archimedes' principle, the buoyant force, it's going to be equal to the weight of the fluid displaced. So mF, that's the mass of the fluid displaced, times g. That's the weight of the fluid displaced, mfg. Now, what we always do with these typically is for the mass, we like to replace that with the density. So density is mass divided by volume, right? And so we can always write the mass as the density times the volume, and we typically do this. So this is going to be the density of the fluid displaced times the volume of the fluid displaced times g. Now, if we're going to get the max value for the buoyant force, then we need to make the volume of the fluid equal to the volume of the raft, because we're going to put it all the way in, right? Now, the raft, it has a volume, because it's a rectangular solid, it's length times width times height, right? And so here we have a thickness here, which is equal to 0.3 meters. And we have an area here, right? 4 by 4. If we multiply those two sides to get the area, we're going to get 16 meters squared, right? And so this is going to be for the raft. It's going to be the area of the raft times the thickness. Let me call this T for thickness. And so we go ahead and calculate this maximum buoyant force. We're going to put in the density of the fluid displaced. It's fresh water, so we know that that's equal to 1,000 kilograms per meter cubed. And then we're going to go ahead and multiply by the volume of water displaced when we put the entire raft in. That's going to be the area of the raft, 16 meters squared, multiplied by the thickness of the raft, 0.3 meters. And finally, we have gravity, 9.8 meters per second squared. If we calculate the maximum buoyant force, we get a number about 47,000 newtons of upward push. How does that compare to the weight of the raft? So Fg, the gravitational weight of the raft, that's going to be equal to, again, we can write this mass of the raft, right? This is going to be m raft g, but in this case, again, density of the raft times the volume of the raft times g. And if we put those numbers in, density of the raft here is 550 kilograms per meter cubed. The volume of the raft, again, is this combination of numbers here. 16 meters squared times a thickness 0.3 meters And finally G, 9.8 meters per second squared. And that gives us a value of 25,872 newtons. Now we can compare these two numbers here. The buoyant force, the maximum we can get by submerging the raft completely, is much bigger than the weight of the raft. As a result, this raft will float. And in fact, if you think about it, when we did this computation, the only things that differed here were the densities. And so ultimately, if you want to determine whether something is going to float or not, compare the densities. If the fluid is more dense, the object will float. If the object is more dense, it will sink into the fluid. Okay, to solve part B here, we are going to be looking at how far into the water does the raft need to sink before that buoyant force is enough for it to float. We are going to try to calculate this value here, h, the distance below the water. And in this case, we're going to be looking at our free body diagram, right? Again, acceleration here is 0. These forces are balanced. We can set them equal. And so the buoyant force is going to be equal to the gravitational force. These two are equal. So we can start like this. Buoyant force is equal to Fg, right? Note this is not the max buoyant force. That's much bigger than Fg for the raft. And we're going to do the same things before. So the buoyant force, we're going to write it as mg, but we're going to use m is equal to rho v. So for the buoyant force, it's going to be the density of the fluid multiplied by the volume of fluid displaced times gravity. And for the raft, that's going to be the density of the raft times the volume of the raft times gravity. All right, and we see we can cancel the gravity out on both sides. And for the volume of the fluid displaced, we can see that it's going to have a height here of h. And the area is going to be the same area here as for the top of the raft, right? That's what we're going to have for the volume of fluid displaced. So we've got rho of the fluid times the height that's in the water of the raft, or the depth of the raft in the water, times the area of the raft. That's going to be equal to the density of the raft times the volume of the raft. We already said that that's the area of the raft times the total thickness of the raft. And that's what we have so far, right? It looks like we can also cancel out the area of the raft in that equation. And now we can go ahead and just solve for the height. So let's go ahead and do that. I'm going to move over here. And so dividing both sides by the density of the fluid, we're going to have density of the raft divided by density of fluid multiplied by thickness of the raft. And we have all those numbers. In fact, the densities are a ratio, so I can ignore the units since they're the same. 550 divided by 1,000, and the thickness of the raft up here, 0.3 meters. Plugging those numbers in, we see that the amount of raft that is below the surface has a depth equal to 0.165 meters. So that it only needs to sink down 0.165 meters into the water until the buoyant force is equal to the weight of the raft, and therefore it floats.